Aloha, this is Roger Brewer. I retired from the Hawaii Department of Health in the fall of 2024. I'm still working as a part-time contractor for that office. This is a presentation I gave to the National Academy of Sciences, Engineering, and Medicine, or NASEM, on September 8th, 2025. This is the committee tasked with the clinical follow-up and care of residents impacted by the JP5 release at Red Hill in Hawaii in 2021. The title of the presentation, Joint Base Pearl Harbor HICM JP5 Exposure Assessment and Technical Basis of the Hawaii Department of Health TPH Tapwater Action Levels. What I want to focus on in this segment of the presentation I gave to NASEM is this latter part, the technical basis of the TPH, or Total Petroleum Hydrocarbon Tapwater Action Levels. The first part of the presentation is the same as I gave in 2023 when I recorded a presentation for the exposure assessment. This is an outline of the presentation I gave to NASEM. What I want to do today is just focus first on the terminology. Also in that presentation, we went through the migration of JP5 jet fuel into and through the Joint Base Pearl Harbor HICM drinking water system. We talked about categories of tap water contamination, chemistry and toxicity of the contaminated tap water, estimates of reasonable maximum exposure concentrations of specific chemicals, petroleum related and other chemicals that were in the water. And then we ended up with the focus on the use of total petroleum hydrocarbon data to assess health risk. And again, that's what I want to do today in this segment of the presentation I gave to NASEM. See references below. First reference is for the Department of Navy. It's a very detailed summary of what happened in the tunnel that caused the release in the first place, up to the point that the jet fuel got into the drinking water well. The second reference in red is the exposure assessment report that I prepared in 2023. It's a recorded presentation on that exposure assessment posted June 28, 2023 to the Hawaii Department of Health recorded webinars webpage. See the address at the bottom. The other two references are for the reference for the evaluation of environmental hazard at sites with contaminated soil and groundwater. This is the general sort of risk assessment guidance we have with the Department of Health. And then the last reference, comparison of H2H, total petroleum hydrocarbon action levels to data for water samples. And we prepared this to better explain how data collected at Red Hill and other places impacted by petroleum should be compared to action levels. For the terminology, the key term we're using here today is TPH, total petroleum hydrocarbons. It's a complex mixture of hundreds of hydrocarbon compounds, and especially in respect to older releases in groundwater degraded compounds referred to as metabolites. As a default, we assume that at least the initial metabolites are as toxic as the parent chemicals. TPH comprises the dominant fraction of petroleum fuels. You see the barrel I have down at the bottom. This was for JP5, gasolines, really diesel fuels. In general, these TPH compounds, it's a big mixture of aliphatic aromatic compounds, we'll look at it in a minute. They make up 90, 95, 99% of what's in petroleum. So it's really critical that you include these compounds when you're assessing health risks. The second term, BTEX, and then NM for naphthalene, methylnaphthalines, benzene, toluene, ethylbenzene, xylenes. These are individual compounds that might be found in fuels. They're generally tested for and assessed separately in terms of health risk. In FSII, that was a big issue with Red Hill, fuel system icing inhibitor. This is something they add to the fuel. It was in the tank stored at Red Hill when the release JP5 occurred, but it prevents ice from forming in the fuel at high altitudes. And for discussion of that, just refer back to the presentation I posted in 2023. The main compound associated with icing inhibitor are just called DIGME, diethylene glycol monomethyl ether. So we'll be talking about that in this presentation. I did with the NASEM group, and it's also included in the presentation I posted in 2023. The use of TPH data to assess the risk posed by exposure to petroleum goes back quite a ways, at least 30 years now. I first got started in the mid-1990s. At that time, the focus when assessing risk was on the individual compounds like benzene or BTEX and a few PAHs. So one thing that was very obvious at sites we worked on and across the U.S. and other areas, that even though the sample data may show these compounds to be below risk-based screening levels, there's still very obvious heavy contamination in the field, in the groundwater, in the soil. The contamination there was all these other compounds associated with petroleum, the other 99% of compounds in petroleum. So obviously these compounds still could pose a potential health risk, something that needs to be done. If you look at the very bottom here, the second picture from the bottom, you see some flames coming out of a backhoe bucket. This is a case I worked on as a consultant, and there was a risk assessment done for the site. It was an old gas station site. It had been cleaned up quite a bit, actually. They tested for BTEX and pHs. It all looked good. They started to redevelop the site. The soil was catching on fire. Well, this was the gasoline itself, probably some aliphatic and other compounds in the soil that had been tested for it. That was the TPH component. This is a big highlight for me, is we need to start focusing on TPH, all these other compounds. So in the mid-1990s, a group got together called the Total Petroleum Hydrocarbon Criteria Working Group. It's headed by the Air Force. The Navy was also a member. A number of states, including Hawaii, were members. I was watching from the outside from Hawaii. A lot of industry experts and consultants. They got together, looked at this TPH fraction of petroleum, and came up with the idea of carbon ranges, to breaking this TPH up in individual carbon ranges to assess petroleum risk. And the ATSDR in the late 1990s actually published toxicity factors for these carbon ranges. So did the Total Petroleum Hydrocarbon Criteria Working Group. And other states came on board. Massachusetts actually started earlier, in Washington, Texas. Massachusetts in particular published toxicity factors for these individual carbon ranges and other constants. You could treat these carbon ranges as you would any other normal chemical. And they simplified the whole approach. In 2000 to 2020, say up to now, USEPA published toxicity factors for these TPH carbon ranges. California also published toxicity factors and also started looking at metabolite chemistry and toxicity. And I was working for the California State EPA at the time, so I got to be involved in that. I moved back to Hawaii 2005. We started to use TPH data for assessing cleanup of UST and other sites. Also started doing a lot of field research into the chemistry and toxicity of petroleum fuels and vapors and metabolites, partial breakdown products, especially of petroleum and drinking water aquifers. Put together case studies and published some guidance on forensics, more detailed study of exactly what was in the water. It's also a group, ITRC, the Interstate Technology Regulatory Council, published guidance in 2018. Hawaii was part of that on the use of TPH to assess risk in case studies. So the point with all this is that the use of TPH to assess risk has been well established over the past 30 years, although a lot of people still haven't caught on to that. What the TPH criteria working group did is they broke the TPH component of petroleum up into a number of carbon ranges. And a carbon range is just a group of compounds that are chemically similar, have similar toxicity. And they assigned a toxicity factor to each one of these groups. Massachusetts really simplified this process by narrowing it down to just 6 different carbon ranges. So if you look at the makeup of different types of petroleum fuel, you can define as gasolines, middle distillates like JP5, diesel fuel, and such, and then fuel oils. Those are your heavy fuels. These different types of fuels have very distinct mixtures of compounds with different numbers of carbons in the molecules making up those compounds. Gasolines are very volatile. So if you look at the very bottom, you see C2 to C12. These are compounds with 2 carbons to 12 carbons, so they're pretty small, pretty volatile, and that's why gasoline is so volatile. Middle distillates like JP5 and diesel fuel are a little bit bigger compounds, starting with around 6 carbons, say something like hexane, up to compounds with 24 carbons. The fuel oils and motor oil and tars and asphalt and such are comprised of hydrocarbons with a lot of carbon. So C20 to C36, the big compounds. So Massachusetts, in particular, narrowed down the description of these different types of fuels into aromatic and aliphatic carbon ranges. Again, groups of chemically similar compounds. For aromatics, and these are compounds made of benzene rings, like methylbenzene. They grouped all the compounds into just two groups: greater than C8, so greater than 8 carbons to 10 carbons, and greater than C10 to C12. Each of these two groups, they may have dozens of compounds in each group. Then they assigned a single toxicity factor, the same as you would for BTEX or something, any other compounds. Aliphatic compounds, they broke into 4 different groups. So there's compounds with just 5 to 8 carbons. This would be something like pentane up to octane. They grouped all these compounds together and assigned a toxicity factor. And then they separated the C8 to C12 aliphatic compounds, assigned another toxicity factor. And then C12 to C18 aliphatic compounds, these are longer and longer chains of compounds. And then the C18 to C36. So these are compounds with chemically similar properties like solubility, volatility, and such. So TPH then is the sum of all these aromatic and aliphatic compounds plus any breakdown compounds within a sample. This is one concentration of TPH, but now we split it up into 4 different groups of compounds. BTEX, pH is individual compounds, usually tested for separately. Then they assign toxicity factors to each one of these groups. Actually, some of the groups they combined. This is the USEPA 2022 publication of toxicity factors for carbon ranges. So what a toxicity factor is below these concentrations or this exposure, this dose, no adverse health effects are predicted after years of exposure. So for example, C5 to C8 aliphatic compounds, EPA published an oral or dermal reference dose for ingestion or getting it on your skin of 5 micrograms per kilogram of body weight per day. In inhalation reference concentration, so below this concentration in the air at this concentration, you wouldn't expect to see any health effects. And you see toxicity factors for the other, just 3 groups of compounds now. They combined the aliphatics, C8 to C18 aliphatics into one group, and also aromatics, they just combined into one group, assigned it all the same toxicity. So this made it really easy now to develop action levels in the same manner as done for BTEX. When you're assessing risk posed by these compounds, the main focus is on young developing children. EPA assumes the default body weight 15 kilograms for children. So that's the kilogram BW you see in the toxicity factors. We'll look at that again in a minute. They also published toxicity factors based on subchronic exposure. So these toxicity factors you see above, you could be exposed at these levels for years. Young children could, according to the toxicologists, they wouldn't experience any health effects. Subchronic toxicity factors, they can be a little bit higher than this, but at this higher dose, this higher exposure, you could start seeing health effects within a few days, a few weeks, or a few months. It was a very useful approach, great idea. The problem was very few laboratories could test a sample and break it up accurately into these individual carbon range compounds and report those. And even when laboratories tried, we found some pretty major mistakes in a lot of the tests we were running at the time. The solution was then to develop a single carbon range weighted toxicity factor for different fuel types in different phases of the fuel, either neat, the pure fuel phase, or dissolved phased or vapor phase fuels. And that's what we started working on in Hawaii and in other states over the last 20 years. Let's look at how that's actually done. This is the carbon range makeup of JP5 fuel. It's the sample that we got provided by the Navy from Red Hill. This is the fuel that was released at the site. So the objective here then is to determine the exact carbon range makeup of the different phases of the fuel. If you look in the middle pie chart here, this is JP5 neat fuel, so the pure fuel itself On the left, you'll see what's called a chromatogram. It's a picture of the fuel taken by the laboratory. They slowly heat the fuel up, and as they heat the fuel up, compounds at different boiling points will come off at different times. So the compounds that are very volatile, very few carbon molecules, will start boiling off and create a peak in the picture early on in the process. And as you start to heat up higher and higher temperatures, the bigger compounds with higher boiling points will come up. So you get a nice picture of what the fuel looks like. It's called a chromatogram. You see for JP5 fuel, the TPH makes up 98.6% of the fuel itself. The BTEX compounds 1.4%. This was the point I made before, where the TPH component, this mixture of hundreds of compounds, makes up, in this case, 98.6% of the fuel itself. So if someone's exposed to this, it's really important that you take this into consideration, this fraction into consideration also, and not just look at BTEX. And if you look at risk assessment of exposure to petroleum, it's actually the TPH component that drives risk in almost all the cases I've ever looked at, not the BTEX. In this case, the JP5 neat fuel, so what was it made of in terms of carbon ranges? Well, 82% of the fuel is made of these greater than C8 to C18 aliphatic compounds. So these long chain compounds with 8 or more carbons in them. And then a smaller portion of the fuel is made up of these aromatic compounds, methylbenzenes and such, 18%. Now, when you put this fuel on water, and we'll look at that in a second, we discussed this in the longer presentation I gave, and we had this tested at the laboratory. Then the aromatic compounds are much more soluble. They'll immediately go into the water. So if you test the water underneath of a layer of the JP5 jet fuel, it's still the main compound you'll see in the water are these TPH carbon ranges. In this case, it's the greater than C8 aromatic compounds. They make up 99.8% of the carbon ranges of the TPH that dissolves into the water. And that makes up 59% of the total compounds that dissolve in the water. And then the BTEX compounds make up 39%. So when we're looking at the exposure assessment, one of the categories of contaminated tap water was just dissolved phase contamination. They couldn't see a sheen. You could probably start to smell something at some point. So this tells us what the chemical makeup was of the dissolved phase contaminants from JP5 in the tap water that residents were probably initially exposed to. It was mostly these greater than C8 aromatics, and now we have toxicity factors assigned to these. The vapors coming out of the fuel, as we discussed how vapors were coming off of Red Hill as they vented the tunnels to try to clean them out. The vapors were going down into the military reservations in Pearl Harbor, so people were being exposed to the vapors. In this case, the vapors coming off the pure fuel were dominated by these aliphatic compounds, again, the greater than C8 to C18 aliphatics, with some degree of addition from the CA5 to C8 aliphatic compounds. So again, we know the toxicity of these compounds. We have toxicity factors. We can calculate a weighted toxicity for TPH in general for inhalation of vapors. We can calculate a weighted toxicity for ingestion of tap water that has a sheen or something on it with the pure fuel in it. And we can calculate a toxicity factor, weighted toxicity factor for dissolved phase JP5 related compounds in water. These are the toxicity factors, or carbon range weighted toxicity factors, TPH. We calculated for JP5. Again, it's just based on these mixtures. It's kind of like ingredients for something. Say you're baking a cake. If you give me the ingredients you're going to use in the cake, how much you're going to use of each one, and I know how many calories are in each one of those ingredients, say per mass, then I can estimate the total number of calories that are going to be in that cake you're going to bake. So it's a similar way when you're looking at toxicity. If I know the carbon range makeup of the petroleum in the dissolved or the vapor phase or in the pure fuel phase, then I can calculate a weighted toxicity factor for that. That's what we did here. These are the chronic JP5 toxicity factors we calculated for dissolved JP5 in the water or dissolved JP5 with a sheen on top, which we saw in some people's water coming out of the tap. So the oral reference dose in this case overall was 10 micrograms per kilogram body weight per day. Now, is the same true for dissolved and the sheen, because they have the same toxicity. See the same type of reference doses for dermal contact, the water getting on your skin, and then inhalation. It's just a concentration there. So above this concentration, if you're exposed for many years, then you would expect to see some health effects. You could. Well, what does this mean in terms of assessing risk? Just to translate this into English, what we do in a risk assessment, we assume that the main person, the group of people we're concerned about protecting are young children, young developing children. So if you protect the children, you're protecting the adults. The default body weight for children used by EPA is 15 kilograms. So multiply 15 kilograms by, say, the oil reference dose for dissolved phase JP5 in water of 10 micrograms per kilogram. Then you come up with a dose of 150 micrograms per day. You see in the bottom here. So what this is telling us is that if a child is exposed to more than 150 micrograms per day of dissolved phase JP5 in tap water, then they could start to experience some health concerns if this was after many years of exposure. We'll look at more short-term exposure in a minute. So how much is 150 micrograms per day? This is one mistake I made in the presentation to NASEM. I had the units wrong. Just think of this, a drop of JP5 jet fuel weighs 40 milligrams. So in this case, we're talking about exposures over 150 micrograms per day over many years could cause some health effects. So this is just a fraction of a drop of JP5 per day could potentially pose health effects over many years of exposure. Again, if you saw the NASEM presentation, I had the wrong units in for a drop of fuel. These are the subchronic toxicity factors of JP5 published by USEPA. So in this case, these are concentrations where you could see potential health effects after days to months of continuous exposure if you start to exceed these. So now the reference concentration, reference dose, say oral for dissolved only, has gone up from 10 to 40 micrograms per kilogram of body weight. See, the other reference doses went up, the inhalation concentration went up. This means that now there's higher concentrations of the JP5 in the tap water, in the air, so you could actually start feeling health effects much more quickly than several years. In this case, it could be several days to several months. Translating this into English again with a 15 kilogram child for dissolved phase only, JP5 and tap water for the oral or ingestion reference dose, it equates to the child being exposed to more than 600 micrograms per day. So above this limit, you could start to see health effects after just days to months of exposures. How much is 600 micrograms? Well, again, a drop of JP5 weighs 40 milligrams. So we're talking about just a fraction of a drop per day exposure to JP5 could start to cause health effects in young children after just days to months of exposure. Add a sheen onto it. The sheen is actually, in this case, less toxic aliphatic compounds compared to what dissolved into the aromatics. But still, even with the sheen, if a child's exposed to more than 1,185 micrograms of dissolved phase JP5 plus a sheen on top of the water per day, then you'd expect to see potential health effects after just days or months of exposure. This gives you an idea of what the residents were exposed to, assuming the toxicity, most of it came from the JP5 at Red Hill in the military bases in the tap water. They're probably the children and eventually adults are being exposed to much higher doses per day than noted here. We have toxicity factors for these carbon ranges, and we can calculate weighted toxicities just for TPH. So we just have to test a sample one time to get TPH. We plug these weighted toxicity factors for TPH and EPA's tap water screening level equation you see here. There's three different segments: ingestion, dermal absorption, and inhalation. You plug this in, plus some other parameters, some solubility and such, and it'll calculate a risk-based screening level for tap water. And above this screening level, then you could have potential health effects. That's what we use in Hawaii. This is a summary of Hawaii's TPH drinking water action levels from 2005 to present for middle distillate fuels. The middle distillates include diesel, JP5, jet fuel, kerosene, compounds like this. So in the year 2005, I first published TPH action levels for tap water. We actually published two different numbers. One is for toxicity and one is for taste and odors. The toxicity-based action level for dissolved phase middle distillate fuels like JP5 in 2005 was 400 micrograms per liter. This was based on an assumption that we're just looking at groundwater that could be used for drinking water, that the petroleum in the groundwater was heavily degraded, which in most cases it is, and no longer volatile, so we weren't looking at inhalation exposure, just ingestion exposure. The taste and odor threshold published at the time for fuels in drinking water was 100 micrograms per liter. This was something published by EPA in 1980. So we compare these two numbers, toxicity and taste and odors. The taste and odor threshold is lower, so it became the final action level, and that of 100 micrograms per liter, again based on taste and odors. So we kept this up through 2017. In 2016, some papers were published that reviewed this taste and odor threshold for petroleum fuels in drinking water and discovered a lot of problems and translation mistakes in the 1980 USEPA document. This is actually based on a study done in the Soviet Union in the 1940s and 1950s. The study was in Russian and Polish. Whoever interpreted it for use in that USEPA document apparently weren't that good in Polish and Russian, and they had mistranslated some parts of it. So we reviewed some other documents available at the time and revised the taste and odor threshold to 500 micrograms per liter. So in this case, the 400 is lower than 500 for toxicity, so the new action level was 400 micrograms per liter based on toxicity. This is actually some pretty important points here. When we thought the taste and odor threshold was 100 micrograms per liter, what this tells us is that people should be able to smell and taste the petroleum in the water before it became toxic, because the threshold was below the toxicity threshold. The taste and odor threshold was below the toxicity threshold. We revised this in 2017. It changed that story. Now the taste and odor threshold is above the toxicity threshold. And actually, we said 500 micrograms per liter. Some people were recommending like 1,000 or 2,000 micrograms per liter. So what this means is that people could be exposed to toxic levels of dissolved petroleum in drinking water without knowing it. They wouldn't be able to taste it or smell it. In 2021-22, after the release at Red Hill, remember early on we were assuming that petroleum was heavily degraded, not volatile anymore, still toxic but not volatile, so you weren't inhaling vapors. It was pretty obvious the JP5 that went through the Pearl Harbor drinking water system was highly volatile. We could smell it in the outdoor air. I was living beside the base. I could smell it and coming out of people's showers. So we had to include the inhalation pathway in that same equation I showed before. So people were being exposed to more petroleum through inhalation. So we had to reduce the toxicity-based action level from 400 to 266 micrograms per liter. And that became the new action level after the Red Hill event. In 2024, we discovered rather belatedly that the US EPA actually had a group of toxicologists looking at the toxicity of these carbon ranges. And in 2022, they published an update to it. We didn't find out until 2023 that concluded these compounds, these carbon ranges, were more toxic than originally thought. So the toxicity-based action level, we put in the new toxicity factors and reduced the toxicity-based action level for these middle distillates, TPH in fuel and drinking water from 266 to 91 micrograms per liter, and that became our final action level. So that's the evolution of the action levels for TPH used in Hawaii. EPA also published subchronic action levels for these carbon ranges. When we use those to come up with the carbon range weighted toxicity factor and action levels for dissolved phase JP5 in drinking water, we come up with action levels if it's purely dissolved of 340 micrograms per liter. This is still below the drinking water threshold. And again, what this is implying is that if people at the base were drinking or consuming tap water with more than 340 micrograms per liter of dissolved phase jet fuel JP5 in it, they could start experiencing health effects within a matter of days to weeks. If there was a sheen on the water at the time too, say it was getting into cooking or even drinking it, then they could start experiencing health effects within a matter of days or weeks if the concentration was over 270 micrograms per liter. This is pretty definitely, I think, what was going on at the base. And again, below the taste and odor threshold, people didn't realize what was happening until it was too late. That was how the action levels were developed. Another key issue we talked about was how you measure TPH at the laboratory. It's not an exact science, but it's the best available at the time. So when you send a sample to the laboratory, they run two different tests on that sample to determine the concentration of TPH, of these petroleum hydrocarbons, in that sample. So they have to test for volatile compounds and semi-volatile, non-volatile compounds separately. The first test is called purge and trap. They bubble nitrogen or some other compound into the sample, and then they catch the vapors coming off the sample. It's kind of like blowing into a soda or something, and you're purging off the carbon dioxide, whatever compounds are in it. And they would capture that and test it, and they could quantify the concentration of volatile compounds that are in that sample. The second test is the solvent extraction method. They add a solvent to the sample. This is after you purge it. And then it's going to absorb or soak up all the semi-volatile, non-volatile organic compounds in that sample. And they can quantify the concentration of these semi-volatile, non-volatile contaminants in the sample. So your concentration of TPH is equal to the sum of the volatile organics that were in the sample and plus the sum of the extractable organics that were in the sample. That's TPH. If you're testing for BTEX and such separately and those separately, which usually are, you can subtract this from the total concentration of TPH reported. It's usually minimal compared to the concentration of these volatile and extractable organics associated with this big complex mixture of compounds. Laboratories will sometimes report three different groups, or they'll test for three different groups of compounds. They call them gasoline range compounds. That's the volatile stuff. Then they break the extractable range compounds into diesel range organics and residual range organics. But to get a concentration of TPH, total TPH in the sample, you still add all three of these together, and then you subtract the BTEX if needed. Then they would look at the chromatogram generated from testing the sample and compare it to chromatograms for different fuels and determine whether it was a gasoline, a middle distillate, or a residual fuel. And that tells you what action levels in DOH guidance you could compare your total TPH concentration to. So there's a big problem with the Navy reports. It was still going on at Red Hill last time I looked, is they're reporting these GRO, DRO, and RO concentrations separately. Maybe reporting them as TPHG gasoline, TPHD diesel, TPHO oil, and then comparing them to DOH action levels for these different types of fuels. Well, that's incorrect. They should be adding these concentrations together. There's only one concentration of TPH in the sample. You look at the chromatogram and determine which type of fuel best fits what was in the water sample, and then compare the action levels to that. Just something to keep in mind for people reviewing the groundwater data at Red Hill. This is just an example of the different fuel fingerprint chromatograms. I've got the JP5 chromatogram here highlighted in red. This is what the laboratory will do. They'll test a sample, they generate a chromatogram, then they compare it to all these other chromatograms, and they can tell you what type of fuel was in the water. And one issue with this is that the chromatograms, the size of the chromatograms, how big these humps are, depends on the concentration. So the higher the concentration, the bigger the hump. Once you get down to a concentration of less than about 200 micrograms per liter, so remember a drop of JP5 weighs about 40 milligrams, there's very little fuel left in the water. The chromatogram is just too small for laboratory chemists to tell you what type of fuel that is, or even if it was fuel. So what they have to do a more detailed forensics testing, look at individual compounds in that sample and determine whether or not those organic compounds they identified were actually associated with fuel or not, and if they were, what kind of fuel. And this is discussed in a guidance we posted in 2024. That was an overview of the TPH. And again, if you want to see the review of how the exposure assessment report itself, look at the June 28, 2023 recording. It's posted even the NASEM webinar that I gave yesterday. And again, with the NASEM webinar, I messed up the weight of a drop of fuel and such. That's something to keep in mind. Just a fraction of a drop of fuel in tap water, if a child is drinking that every day, could pose both, long-term and even short-term health effects. So they could start experiencing health effects very quickly within a matter of days. The concentrations they were exposed to, some of the kids were getting sick within a matter of minutes or hours or such. So it had to be really high doses that they were being exposed to. The last question we looked at in the webinar was, were people being exposed to contaminants in tap water prior to the November 20th, 21st release? Catherine McManahan looked at those, and also Eva Davis, who wasn't able to attend. They'll be looking at this in more detail later. I know ATSDR has a group. I just wanted to show you these two chromatograms. I talked about this in the original exposure assessment report I posted. These are samples collected from the Red Hill, from groundwater underneath the Red Hill facility. The first was the monitoring well number 2, the most contaminated well under the fuel tanks. They've known it's been contaminated for 20, 30 years. But in this case, the laboratory reported a concentration of, I call it high boiling point, high range organics of 530 micrograms per liter. If you look at the chromatogram, all that mass, all that concentration is coming from these 3 humps that you see. They're reporting it as residual range organics. And the Navy, in their report, they reported it as TPH oil. I showed these chromatograms to some pretty top-notch petroleum chemists, and they all concluded these humps you see highlighted in red, that's not oil. So what was that in the groundwater? On the right is a sample taken on the same day from the Red Hill shaft faucet. This is the water that's going directly into the Joint Base Pearl Harbor Hickam drinking water system, and there those 3 humps are, again, the same thing. They're reported for that sample as residual range organics, high boiling point organic compounds, 480 micrograms per liter. So these compounds, that what should have happened at the time, what should happen when the labs should do, the Navy should do, again, is when these high boiling point compounds get reported, is they need to do more detailed analysis to find out exactly what these compounds are. In this case, we're really not sure. At first, we thought maybe this is degraded fuel. It's been on the tanks in the groundwater for decades or something, but the chemist I showed it to said this doesn't look like degraded petroleum. So what are this? This surfactants, because we know they used different solvents or cleanup compounds in the tunnels after release. Or is it an artifact of laboratory processing? One laboratory chemist told me that's what it could be. Is it algae or something else? All we can say is it's organic material. But it's something to look at in more detail, especially with these high boiling point compounds. When they show up, the laboratory needs to look at it in more detail. They can run more detailed analysis. We discussed this in our forensics guidance we posted in 2024. That was the presentation. Again, I just focused this case on the TPH. I wanted to go into more detail, give a better explanation than I did discussion with the NASEM group. So any questions? I know NASEM is still taking comments and questions on that presentation. And the Department of Health, the Hazard Evaluation Emergency Response Office, have new toxicologists groups there, John Jacob and Weila Lee. They'd be good to contact to also have questions, and as needed, they can get in touch with me. So thanks again. I'm sure we'll be looking at this for many years to come.